Today, I'm going to be showing you some complete examples of how to find the homogeneous transformation matrix from the base frame to the end effector frame. We learned previously that this homogeneous transformation matrix consists of a rotation matrix, which is 3 by 3, with 3 zeros underneath it, and then the displacement vector, which is 3 rows and 1 column, with a 1 at the bottom. We learned that this displacement vector tells us the location of the end effector in the base frame. Today, we're also going to be learning how to do something called coordinate transformation. This means that we can use the homogeneous transformation matrix to find the location in the base frame of any object that the robot end effector might be holding. We can do this by simply multiplying the homogeneous transformation matrix by a point x, y, z with a 1 at the bottom, telling us the location of an object in the end effector frame that the robot is holding. This XYZ data point, that is the location of an object the robot is holding, is generally written as a capital P, and as a superscript we write the frame that this point is in. This point consists of not only X, Y, Z, but also it has the number 1 tagged on to the bottom. So let's take a look at some examples now so you can see how this works. For our first example, let's take a look at a spherical manipulator. Now I've drawn this spherical manipulator with an offset over here just so that I can show you how we deal with that in our homogeneous transformation matrix. So the first thing I'm going to do is draw in the coordinate frames. I make sure that Z is the axis of rotation and that the overall frame follows the right-hand rule. And for the prismatic joint, I need Z to be the direction of motion. And then for the end effector frame, I just copy the frame that comes right before it. Next, I need to label the joint variables. For the revolute joints, I make sure that these joint variables follow the right-hand rule. And I number the joint variable to indicate which frame that joint variable affects. Lastly, I need to go back and label all of the link lengths. Now, I can go ahead and find each of the homogeneous transformation matrices. I'm going to need to find 3 of them here. I need one that goes from frame 0 to frame 1, one that goes from frame 1 to frame 2, and one that goes from frame 2 to frame 3. To find this matrix, I need to find the rotation matrix, and then put 3 zeros underneath it, and then I'll need to find the displacement vector and put a 1 underneath it. Let's start by finding the rotation matrix part. The rotation matrix has to start out with a matrix that shows how frame 0 can be rotated to get it into the same orientation as frame 1. I look and see that there is one axis that is the same between these two frames. That means that I could rotate frame 0 around its x frame to get it to match frame 1, because the two x-axes are in the same direction here. I could write this rotation as a 90-degree rotation around x. However, I'm also going to show you here a shortcut that we can use to get this rotation matrix that shows how the two frames are oriented relative to each other. Here's how this shortcut works. Each of the columns of this rotation matrix represent the axes of the frame we're going to, or in other words, our new frame. The first column represents the new x-axis. The second column represents the new y-axis, and the third column represents the new z-axis. Each row represents an axis of the old axes, or the frame that we are coming from. The first row represents x, the second row represents y, and the third row represents z. Now, here's how we can fill in this matrix. I look and see that my new x-axis is in the same direction as the old x-axis. So I put a 1 in the intersection of the new x and the old x. Next, I see that my new y-axis is in the same direction as old z. So I can go and put a 1 in the intersection of new y and old z. Lastly, I see that the new z-axis is in the opposite direction as the old y-axis. So I can go and put a -1 in the intersection of new z and old y. Now I go in and fill in zeros for all of the other places in this 3x3 matrix. This gives me the same result that I would get if we had gone and gotten the rotation around x matrix and filled in 90 degrees. Now, I'm not yet finished with my rotation matrix because I haven't yet accounted for the joint variable θ1. So I need to make sure and do that. The way we do that is by left multiplying by a θ1 rotation around z. So I'm going to take this matrix and move it over so I have room to put a rotation around z. I'll slide it down here. I'll put my rotation around z on the left. Now, to get my final rotation matrix, I have to multiply these two together. I'm going to multiply them together and just fill them in to my homogeneous transformation matrix. So to get the value that goes in row 1, column 1, I'll multiply together row 1 and column 1. So 1 times cosine θ1 plus negative sine θ1 times 0 plus 0 times 0 gives me cosine θ1. And I continue doing this, so for the second row, I'll multiply row 2 times column 1 and get sine θ1. And then I'll multiply row 3 times column 1, which gives me 0. I next multiply row 1 times column 2 to get 0. Row 2 times column 2. Row 3 times column 2, and then I'll move on here. And I'm finished with the rotation part. So I can now move on to the displacement vector part. The displacement vector from frame 0 to frame 1 is this vector right there. So I'm going to have to account for both A1 and A2 in this displacement vector. Remember that this vector that I write has to be true regardless of the rotation theta 1. So if I imagine looking at this from the top, we can see that what we'll get is a triangle where here's x0 and here's y0. If I'm looking at this from the top, that's how these axes will look. And then here is A2, and this is the center of frame 1. And this is the rotation theta 1. So the x value of the displacement will be equal to A2, the hypotenuse, times the cosine of theta 1. The y value of this displacement will be equal to A2 times the sine of theta 1. And the z displacement we can see from our three-dimensional figure here will always be A1, no matter what the rotation of theta 1 is. So I fill in A1 here. And we're done with H01. Let's move on to find H12. We'll start by finding the rotation part. Let's use our little trick for finding the part of the rotation that accounts for the different orientations of these frames. So up here I'll write new, this is x, y, z, and over here this is for the old axes x, y, z. My new x-axis is in the opposite direction as the old z-axis. So I put a -1 in the intersection of new x and old z. The new y-axis is in the same direction as old y, so I put a 1 in the intersection of new y and old y. And my new z is in the same direction as old x. So I put a 1 at the intersection of new z and old x, and then I fill in zeros. What we get here should be the same result that we would get if we had taken frame 1 and rotated it 90 degrees around y, which would get this frame to match this one. So I'm not yet done with my rotation matrix because I still have to account for the rotation theta 2. And the way we account for that is by left multiplying by a rotation of theta 2 around z. I'm going to multiply and fill in the result in my homogeneous transformation matrix. And of course I have to fill in zeros at the bottom. Now I'll have a 1 down here, but I still have to find the displacement vector part. The displacement vector is this vector right there. And when I write this vector, it has to be true no matter what the rotation of theta 2 is. So as theta 2 rotates, the center of frame 2 is going to move up here in the plane of x1, y1. The x component of that vector, this component, is going to be equal to A3 times the cosine of theta 2. The y component of the vector will be A3 times the sine of theta 2. And there is never any z component of this vector, no matter what the rotation theta 2 is. so that becomes a 0. And here we're done with H1, 2. I'm going to take these matrices that I finished and put them down at the bottom so we have some room here to work out our last homogeneous transformation matrix. Okay, let's find H2, 3. And we'll start this out by finding the rotation part. R2, 3. Now we have to start out by writing the matrix that represents the change in orientation between these two frames. Since these two frames are already in the same orientation, we use the identity matrix. Now, by applying the trick that we used in the past two rotation matrices, can you see why this rotation matrix means no rotation? This rotation matrix is saying that the new x-axis is in the same direction as the old x-axis, and the new y-axis is in the same direction as the old y-axis, and the new z-axis is in the same direction as the old z-axis. In other words, no rotation. Now here, we are finished with our rotation matrix because there is no rotational joint variable to be accounted for here since we have a prismatic joint. So I'm going to go ahead and fill in this rotation matrix in my homogeneous transformation matrix. And fill in zeros at the bottom. Next, I need the displacement vector part. The displacement vector is right here. And this has to be true no matter what the value of D3 is. So this displacement is in the z direction, and it's always in the z direction, no matter what value we give to D3. So there's no displacement in x and none in y. In z, we have the displacement both of the joint variable D3 and the link length A4. So we say A4 plus D3, and then we have to put a 1 here at the bottom. And here we are finished with our last homogeneous transformation matrix. So we've now found all three of the matrices that are necessary. To find the complete homogeneous transformation matrix all the way from the base frame 0 to the end effector frame, frame 3, we have to multiply these three matrices together. So h from 0 to 3 is equal to h from 0 to 1 times h from 1 to 2 times h from 2 to 3. I'm going to write out the matrices that we've found here. Now, matrix multiplication is associative, which means that it doesn't matter which of these two matrices we multiply together first. We could multiply these two matrices and then multiply the result by the one on the right. Or we could multiply these two matrices together and then multiply the result by the one on the left. Whatever way you want to do it is fine. I'm going to multiply the two on the left first. So I started by multiplying this column here, the first column, by the first row, and then the second row, and then the third row, and then the fourth row, and that got me this entire column. Next, I'll take column 2 and multiply it by each of the rows to get my next column. Column 3 by each of the rows, and column 4 by each of the rows. Now I still have to take this matrix and multiply it by this one. I'm going to shrink my matrix so that I have a little more room. So we're going to do this matrix multiplied by this one. So this column times this row, this column times each of the other rows will give me the rest of this column. Then column 2 times each of the rows. Column 3 times each of the rows. And finally column 4 times each of the rows. And there we go. We have the complete homogeneous transformation matrix from frame 0 to frame 3. This matrix allows us to calculate the position of the end effector in the x direction, here, the first element, in the y direction, here, the second element, and in the z direction, here, the third element, for any values of my link lengths and my joint variables. But it also allows us to do another thing called coordinate transformation. Coordinate transformation allows us to find the position of anything that the robot might be holding in its end effector. So I'm going to go back up to the kinematic diagram here. Let's suppose that the end effector of this robot is a chair and there's a person sitting in the chair. So I'm going to draw a person here. Let's say here's the chair, let's say like that. And let's suppose there's a person here sitting. And suppose that this is some kind of a ride where we're going to be moving this person around. We know the location of this person's head in the end effector frame. I'll call that capital P, and I'll put a 3 there indicating that this is a point in the 3 frame. Suppose we know that the location of that person's head is at 0 in x3, and let's say it's at 3 feet in y, and in z it's 0, and we have to add a 1 always at the end of this vector. We can figure out where that person's head is located not in the 3 frame but in the 0 frame by multiplying this vector times our homogeneous transformation matrix. I'll multiply by this point in the 3 frame, which was 0, 3, we're using feet here in this example, 0, and then there always has to be a 1 at the bottom. Now when I multiply this vector by this matrix, it will tell me the point in frame 0. So I'm going to do this multiplication just so that I can show you how this works. So I start by multiplying this vector times row 1 plus this entire thing, because that gets multiplied by 1. Then for the second row, I take this vector and multiply it by row 2. Then this vector times row 3. And then this vector times the 4th row, which should always end up just being 1. Now, this tells us the x, y, and z positions, not of the end effector, but of the person's head in the chair. You can probably see why this is a really useful and important thing to be able to do. We could figure out the location of the head of the person who's currently sitting in the chair for any values of the joint variables and link lengths, but we could also predict the locations of the head of somebody else who's taller or shorter sitting in the chair in the robot's end effector. This is a useful thing for preventing disaster so that we don't hurt anybody, and also for predicting the locations of an object that a robot might pick up, or the end of a welding tool that a robot is holding, or the end of a paint sprayer can that we might put into the robot's end effector. We can use this approach to find the location of anything that we know the position of relative to the end effector and find out where it is in our base frame or world frame coordinates.